Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be continuing our discussion of motional EMF. In the previous video that I made for these, we had a conducting bar or rod moving through a magnetic field, and we considered what happened to individual charges within that rod as a result of moving through the magnetic field. Today, we actually want to continue that by placing the bar on a pair of conducting tracks. So our geometry maybe looks something like this. The resistor that connects the end of these tracks is merely taken to have a resistance large compared to that of the tracks. So we have conducting tracks, and we could say maybe they have negligible resistance, and maybe the bar does as well. And so essentially the main resistance is here at the end. Now we know that as this bar is moving through this magnetic field, a charged particle within the bar is going to experience some amount of force from the magnetic field. Specifically, the force on this particular charge will be in this direction. And so essentially what we would expect is that the bar itself, if I were to draw like a blow up of the bar, so that we see kind of the two ends of it, these positively charged particles should be moving to one end of the bar. Negatively charged particles should move to the other end, and we should, as a result, get some sort of an electric field between the two ends of the bar, which more or less looks like this. And that electric field then balances out additional moving charges. So an additional charge within the bar sees a force towards the plus side, if it's a positive particle, from the magnetic field, and towards the minus side from the electric field. And that was the case of a bar just moving through without the conducting tracks. But if we have conducting tracks, then when this particle makes its way here, it actually is allowed to just kind of continue through the tracks. And so I end up expecting to see a current round and round and round like this, induced in the closed circuit, essentially. And so this is an electromotive force, not just a voltage drop, because it is able to essentially apply a current to the system that it's within. Okay, so we know how much force, we know how much field, all that. The equilibrium condition before was that the induced EMF, E induced, should be V times L times B, or V cross B times L. So VLB times sine of angle theta, where we can draw, let's say, the magnetic field. If we were to rotate everything a little bit, we could draw velocity here and magnetic field here, and so your angle theta is between these two vectors. Okay, but we should notice in looking at this same diagram again that if I go back to it, if I kind of remove some of the clutter from it and just look at the diagram as a bar moving within a set of rails, that as the bar moves to the right, the sort of enclosed area, so maybe we call this right here an enclosed area A. The enclosed area for this bar tracks end is going to increase just a little bit. So if the bar has moved from, say, this location to this location right here, then I have an increase in the area by essentially a delta A. And so this shaded, green shaded part, this would be like delta A. And since the area itself, A, is given by, let's say, x times y. It's a rectangle, so this right here would be x. This right here would be delta x. Area is x times y, and delta area, therefore, is delta x times y. And so if I were to sort of reframe this induced EMF, see, I've said that it's VLB sine theta. Remember that V is defined as above as delta x over delta t. So this kind of implies that my induced EMF, again, the L vector right here, would become a y vector. So my induced EMF is V times y times b times sine theta. This could just as easily be b times y is delta x times y over delta t is the same as delta area over delta time. And so this means that my induced EMF be written as delta A times B over delta T. And then we have that sine of theta. But since I've kind of removed the velocity vector, we might instead use an area vector here. And so my induced EMF become delta A over delta T B times cosine phi, where phi is the angle between the area vector. Recall that the area vector always points in a direction perpendicular to the direction of the plane in which the area is being found. So this would be my delta A. This suggests that my induced EMF is actually B dot delta A. So either of these is a valid way of expressing that same induced EMF. And so my area vector, therefore, that cosine term, essentially, if I rotate everything, I have a B field here, and then I have an area vector, which let's skew it slightly, like so. Then phi would be the counterclockwise angle between area vector and magnetic field. So that's what defines phi for us. Now, as it turns out, there's an additional minus sign that can be tagged onto this. And also, as it turns out, if I do this with multiple sets of tracks, rails, etc., like n of them, I can throw an n into this equation. But that one's a little bit more tricky to envision. So let's do a quick example and then we'll call it a day. And actually, before I do the example, maybe a couple of comments are warranted. The first comment is that this changing area over changing time is actually valid even if you don't have a moving coil. So if you have, I don't know, like let's say a winding of wire that you're able to push on so that the geometry goes from circular to like elliptical maybe, and the area therefore changes. then this would also enable you to induce an EMF, or at least so these equations would suggest. It also suggests that if you rotate the coil of wire relative to the field, you should get an induced EMF. The second comment is, why did I bother with having a resistor on the end? The resistor is so that via Ohm's law, we could write that the current induced is the induced EMF divided by resistance. So with those two little caveats said, we're ready for our example. So let's say that we have a coiled wire with 10 turns, each encloses some known area, and we squeeze the wire so that the enclosed area is reduced from 0.6 square meters to 0.25 square meters. But this whole process of squeezing takes 2 seconds to accomplish. So if in the nearby region we have a uniform magnetic field of 1.5 Teslas, which is perpendicular to the coil's axis, then we want to determine the induced EMF. Basically, we have some wire that's like this, and we are changing it to be more like this, so that it's smaller enclosed area. Our magnetic field in this case is basically just like this in the region of interest. So this would be perpendicular to the plane containing the wire, or it's oriented basically like along the coil's axis. I kind of miswrote this. This should actually say parallel to. If it's perpendicular to, then the answer here is 0. So if it's parallel to, then that means that the angle phi is essentially 0 or 180 degrees. And so what that does is it means that we have a non-zero induced EMF. So phi is 0 degrees. Delta A is 0.35 meters squared. That's 0.6 minus 0.25. Or we could maybe say it's negative 0.35 since we started big and ended small. Delta time in this case is 2 seconds, and our magnetic field is 1.5 Tesla. So the induced EMF is B delta A over delta T cosine phi. And so that ends up looking like 1.5 Tesla times 0.35 square meters. And we actually don't care about the sign in this case. That'll be for a different lecture. Divided by 2 seconds times cosine 0 degrees. So if you multiply all those things together, what you end up getting is 24.75 excuse me, 0.2475 volts. Excuse me, I said 24. It's a 0.2625. So 0.2625 volts is your induced EMF average. That's it. That's all for today's video. So hope you learned something from it, and thanks for watching.